Today we will be discussing the power flow diagram, the torque and power equations, and losses and efficiency in the case of a three-phase induction motor. The power flow diagram shows the stages of power conversion. The power input given to the stator after deducting all the losses from the input power, we have the actual output power or shaft power. To the three-phase induction motor, we are providing a three-phase supply. So the input that is given to the stator winding is electrical in nature. So you'll have to reduce the losses on the stator, and the diagram it is given as stator copper loss and stator iron loss. The rest of the power is available as air gap power, or that is the actual input to the rotor circuit. Again, from the input to the rotor, we will have to reduce rotor copper loss, then rotor iron loss. The rest of the power is converted to mechanical power. Now we will have to consider the mechanical losses, and after deducting the mechanical losses, the output is available from the motor that is given as power output or shaft power output. So in the equation it is given power input to the stator, that is the electrical input, is given as root 3 V1 I1 cos phi 1. It is denoted with a subscript 1 because we consider the stator to be almost equivalent to the primary winding of a transformer. And after considering the losses, that is WCU1 and WI1, that is the copper loss on the stator and iron loss on the stator, we have the air gap power given as PIR or PG. So when we consider the input to the rotor side, after deducting the stator copper loss and stator magnetic losses from the input power that is given to the stator winding, there will be a torque that is produced or developed, that is given as TD. And we can write the input power to the rotor PIR in terms of TD as 2 pi ns TD divided by 60. Remember the equation, power is equal to torque into omega. Power is equal to 2 pi nt divided by 60. Now we will have to consider the losses on the rotor side, that is rotor copper loss and rotor iron loss. Rotor iron loss will be negligibly small because the frequency on the rotor side will be very small. We have the equation Fr is equal to Sf, and since on running condition the slip is very small, we can consider the frequency of the current on rotor circuit will be very small, and correspondingly the iron loss can be neglected. So we can write the power developed is equal to PIR, the power input to the rotor, minus the copper loss on the rotor side, that is PIR minus WCU2. Since the rotor is running at a speed n, considering the torque that is developed TD, the power developed can be written as 2 pi n TD divided by 60. So from the power developed, we will have to reduce the mechanical losses given as Wm, and we get the power output PO equal to PD minus Wm. And if the actual output torque or shaft torque that is available is T, we can write the power output as P0 or PO is equal to 2 pi nt divided by 60. Now we'll write the equation for the power. So we have the developed power in terms of TD as 2 pi n TD divided by 60 and power output as 2 pi nt divided by 60. So power output is equal to power developed minus the mechanical losses. Wm is equal to Pd minus Po from the above equation, and from the equations of Pd and Po, Wn can be written as 2 pi n Td minus T divided by 60. From the previous slide, we have the air gap power PIR or PG is equal to 2 pi ns Td divided by 60. So the rotor side copper loss can be written as air gap power minus PD, that is PIR minus PD. And when we rewrite with the equations of PIR and PD, we get the expression for the rotor side copper loss as 2 pi into ns minus n divided by 60 into Td, and ns minus n is equal to SNS, and we have the equation WCU2 equal to S 2 pi ns Td divided by 60, that is equal to S into PIR. So the secondary side copper loss is equal to S into air gap power. Rewriting the equations, we have the developed power PD is equal to air gap power into 1 minus S. The ratio of the powers PIR, WCU2 and PD can be written as 1 is to S is to 1 minus S. Similarly, we can obtain an equation for PD. The power developed is equal to air gap power into N divided by Ns. Also, the copper loss on the rotor side can be written as PD, the power developed, into S divided by 1 minus S. We have the equation for the percentage efficiency as P output divided by P input, that is 2 pi nt divided by 60 divided by root 3 V1 I1 cos phi 1 into 100. The torque is developed because of the internal electrical to mechanical power conversion. And we can write the developed torque in terms of air gap power as well as in terms of developed power. Only thing is that in both the equations we will have to consider different speeds. That is, if it is written in terms of air gap power, we will have to consider the stator rotating magnetic field speed, that is the synchronous speed. And if it is written in terms of developed power, we will have to consider the rotor speed n. So we have the equation TD is equal to PIR divided by 2 pi ns divided by 60, and TD is equal to PD divided by 2 pi n divided by 60. The actual shaft torque or the actual torque available as the output can be written in terms of power output as PO divided by 2 pi n divided by 60, or T is equal to TD minus TL, where TL is the elapsed torque. So in three-phase induction motor, we will have to consider different torques. The shaft torque means there is a torque that is available as the actual output from the machine, and the lost torque is the torque or the power that is lost due to the windage and frictional loss or mechanical losses. Slip power is actually the loss in rotor side mainly because of the rotor copper loss, and air gap power is the torque that is available or converted from the stator side to the rotor, and it is also called as torque in synchronous watts. The definition for synchronous watts is the torque which develops a power of 1 watt when the machine is running at synchronous speed. In the power flow diagram of three-phase induction motor, we had seen the losses that occur on rotor side as well as stator side, that is in energy conversion. We will see once again one by one different losses in three-phase induction motor. The first one is magnetic iron or core loss, that is considered to be a constant loss. We have to consider the magnetic losses on stator as well as rotor, and we have two types of magnetic losses, that is hysteresis loss and eddy current loss. And the hysteresis loss can be reduced by using silicon steel material. The equation is given as eta Bmax raised to 1.6 FV, where eta is the hysteresis constant, Bmax is the flux density, maximum flux density, and F is the frequency, and V is the volume of the material. And we can write WH is proportional to V raised to 1.6 F, and that is because Bmax is proportional to V, where V is the voltage. Whenever we need to consider the hysteresis loss on the rotor and stator, we will have to consider the corresponding frequencies. If it is stator, frequency will be F, that of the supply, and if it is rotor, it will be Fr, that is equal to slip into F. Second part of iron loss or core loss is eddy current loss, that can be reduced by using thin laminations, and the equation is given as W is equal to K Bmax square F square T square V. Again in the equation, V is the volume of the material, T is the thickness of laminations, F is the frequency, and Bmax is the maximum flux density, and K is eddy current constant. And we can write W is proportional to V square F square, where V is the voltage. We had already seen Vmax is proportional to V the voltage. And here again we will have to consider the stator side and rotor side eddy current loss, and for the same we will have to consider the corresponding frequencies. And the thickness of lamination on the stator side will be of the range 0.35 mm to 0.45 mm, and preferably 0.35 mm for 50 Hz. And on the rotor side, we can even increase the thickness of the lamination because the frequency on the rotor side will be less. And altogether, when we consider the core loss, the rotor side core loss or iron loss can be neglected because the frequency will be very less compared to the stator side frequency. Since in the case of three-phase induction motor, the supply voltage V and the frequency F are constant, we can consider the core loss in three-phase induction machine to be a constant. The second set of losses is electrical loss or copper loss or ohmic loss. It is a variable loss. We will have to consider the resistance of the rotor conductors and stator conductors, and we have the rotor copper loss and stator copper loss given by the equations 3I1 squared R1 and 3I2 squared R2, where I1 and I2 are the stator current and rotor current respectively, and R1 and R2 are the stator resistance per phase and rotor resistance per phase. Since I1 and I2 are varying depending on the load on the machine, we will have to consider the copper loss to be a variable loss. The third set of losses that can happen in induction machine is the mechanical loss. Here we will have to consider the frictional loss as well as windage loss. And frictional loss is the loss that occurs between two solid parts, and windage loss is between a solid part and the air. Frictional loss is proportional to N and windage loss is proportional to N square. And here again, if we consider the machine to be operating at a constant speed, we can consider the mechanical losses, that is friction, as well as windage loss, as constant loss. Induction machine is a rotating machine, and we can find the efficiency of the machine is of the order of 85%, and the percentage efficiency is given by the equation P output divided by P input into 100. Till now we are discussing the equations for power and torque and the relation between different torques and different stages of power output, and we had seen the losses that are occurring in three-phase induction motor, constant as well as variable losses, and the efficiency of induction motor. Hope you have understood. Thank you.